Fins are often used in heat exchangers to improve the rate of heat transfer in a given device by increasing the cooling surface area. Fins can be expensive to add to a device, therefore optimizing the size and material of the fin is extremely important. Pin fins were chosen with a rectangular and triangular cross-section for the two geometries. Both fins were modeled using aluminum and copper.
The fins were modeled in Ansys as being of effectively infinite length. The results from Ansys were compared to standard textbook equations, using a temperature at the base of 150 degrees Celsius and a bulk temperature of 20 degrees Celsius. These equations were used to compare the overall heat transfer of the fins and the temperature difference along the fin. Sort of both.
The fins were created in Ansys using the volume tool, represented by a tetrahedral 10-node element. The mesh tool was used in order to create the mesh for the object using the smart size option. Values for the smart size ranged from 4 to 6, and we also experimented with various different elements to represent the model, and negligible difference was found.
The model was created using the appropriate values for isotropic thermal conductivity, and thermal loads were applied to the fins: 150 degrees constant temperature at the base, and convection of 50 watts per square meter on all exposed areas of the fin, using a bulk temperature of 20 degrees C.
The fin length was adjusted until the end temperature of the fin was within 1 degree C of the bulk temperature. A contour plot of the nodal temperatures was used to look at the various temperatures along the fin. In addition, the total heat flow was looked at to find the heat transfer in watts for the fin.
Comparing the overall heat transfer predicted by the fins by Ansys and by the textbook equations, we found very low percentage errors. We also looked at the temperature at the ends of the fins predicted by Ansys and found the location on the fin that the same temperature would occur at as predicted by the textbook equations, and found slightly larger errors of about 10%.
A few key takeaways from this project are that a fin with the largest cross-sectional area and perimeter have the largest amount of heat transfer. Also, materials with higher conductivity will need to be longer in order to reach the same steady state temperature. Finally, Ansys is a good model for optimizing fin designs. As you can see below, most of the heat transfer occurs in the first third of the pin, and it would be very efficient to cut off the second 2/3 of the fin.